Okay, welcome to the first class on flipping the lesson. So what this means is tonight you're going to look at the notes, you're going to look at the book, look at the video. You don't have to do the homework at home. We're going to do the homework tomorrow in class. And so bring your book to class tomorrow. We'll be taking a look at those problems that are assigned as homework. The section we're going to look at is section 4-6 called Linear Programming, and it deals with looking at the constraints on a system to try and optimize profit or cost. So we want to look at a maximum profit or a minimum cost model in this particular section. So linear programming is a technique for optimization of a linear objective function, which is subject to linear inequality constraints. Linear programming determines the way to achieve the best outcome, such as a maximum profit or a minimum cost. So let's look at a couple of those keywords there. One is the idea of a constraint, and a constraint is a linear inequality that restricts the variable to only certain values. So this is a restriction or a limitation. Okay. The other word we need to take a look at is optimization. The idea of optimization is to achieve the best outcome. If you're in business, that means you want to maximize profit, minimize cost, because you want to make the most money as possible. Okay, so let's take a look at one of these systems, or at least the graphing of the constraints. You have 4 inequalities, so you need to graph the regions so that you can see where this is. For x is greater than 0, you have this vertical line. So to the right of that line is where x is greater than 0. Then you have y is greater than 0. So again, when you graph that, you're actually looking at the first quadrant then. Okay, let's look at graphing the other 2 equations. 3x plus 2y is less than or equal to 12. When you put that in slope-intercept form, you get y is less than or equal to negative 3/2 x plus 6. So you can go ahead and graph that line, put in the y-intercept, then apply the slope, and go ahead and put in that line. If we look at the second equation, x plus 2y is less than or equal to 8. When we solve that for y, we get y is less than or equal to negative x over 2 plus 4. So using the y-intercept, go ahead and sketch in that line. Okay. And what you're going to be looking for is the region bounded by these 4 lines. We've already established if it's greater than x and greater than y, it's going to be in the first quadrant. But with the other 2, y is actually less than. So the region that we're looking at is going to be this region bounded by the x and y axis and those lines. When you look at this, an important feature that you need to understand is where are the vertices for this particular system. I have one here at 0, 0, one at 0, 4, one at 4, 0, and then here at 2, 3. And the region in which we're going to find the system has a maximum or a minimum is going to be at these vertices, and we'll see that in just a few minutes. when we take a look at maximizing and minimizing. But first, let's take a look at writing the constraints for a system. In this problem, it says, Jules is in the business of constructing dog houses. A small dog house requires 8 square feet of plywood and 6 square feet of insulation. So that's one piece of information that we have. A large dog house requires 16 feet of plywood and 3 feet of insulation. Now here are some limits. Jules has available only 48 square feet of plywood and 18 square feet of insulation. It says write the constraints on the number of small and large dog houses that he can build with the available supplies and graph this solution set in the system of constraints. So we're going to graph this after we come up with a table. So let's look at this. What are the two things he's building? Large dog houses and small dog houses. So let's set up a table. We have small dog houses and we have large. The other thing we have is plywood and insulation. Okay, we have to define our variables. So let's look at calling small dog houses X. So we're going to let X equal the number of small dog houses and Y equal the number of large dog houses. So when we look at this, for plywood, I need 8 square feet of plywood. So for every small dog house, I will need 8 square feet of plywood, and I will need 6 square feet of insulation. For large dog houses, I will need 16 feet of plywood and 3 feet of insulation. Now I need to think about what's my limiting factor, and that is that I only have 48 feet of plywood and 18 feet of insulation. So let's look at writing our constraints. Okay. We always have to remember, is he going to produce less than 0 small dog houses? No, that doesn't make sense. So X will be greater than or equal to 0. Is he going to produce less than Y? No. Or less than 0 large dog houses. So Y is also going to be greater than 0. So we're going to be looking in this region, again in the first quadrant. So we're to the right of the X equals 0 and above Y equals 0. The next constraint we have to look at is plywood. He's going to require 8 square feet of plywood times the number of small dog houses he builds, plus 16 square feet of plywood times the number of large dog houses he builds. But the combination of those two has to be less than or equal to 48. So if we solve this system, we have Y is less than or equal to negative X over 2 plus 3. So take that equation, put it in slope-intercept form, and go ahead and graph that line. So there's the line that uses the constraint on plywood. The next line is going to be insulation. So 6 square feet of insulation times the number of small dog houses he builds, plus 3 square feet of insulation times the number of large dog houses he builds. And he's limited to only 18 square feet of insulation. So putting this in slope-intercept form, we get y is less than or equal to negative 2x plus 6. So go ahead and graph that. My y-intercept is at 6. My slope is negative 2. So I can go ahead and sketch in that line. So now my region is going to be right here, bounded by the x-axis, the y-axis, and those two lines. So get your vertices, one at 0, 0, one at 0, 3, one at 2, 2, and one at 3, 0. So that's the number of combinations of dog houses that you can build is in that purple region. Okay, let's take a look at the idea of maximizing or minimizing this system. The maximum or minimum value of a linear function subject to linear constraints occurs at a vertex of the region determined by the constraints. So now you can see why we chose to get those vertices, because that's what we're going to use for our constraints. So now maximizing or minimizing, if a small doghouse sells for $15 and a large doghouse sells for $20, the total revenue in dollars from the sale of X small and Y large doghouses is given by the function R of xy equals 15x plus 20y and is called the objective quantity. Since R is determined by or is a function of both x and y, we use the function notation that was introduced in section 3.5, and we write R of xy in the plane R. So the equation R of xy equals 15x plus 20y is called the linear function of x and y, because the revenue is based on the combination of doghouses that are sold. Any ordered pair within the region shown is a possibility for the number of doghouses of each type that could be built, and so it's in the domain of the function R. So how many of each type of doghouses should be built to maximize the revenue and to satisfy the constraints? So let's take a look. We know our function is R of x, y is equal to 15x plus 20y. So now we want to look at those vertices. We can look at R of 0, 0. I'm not sure that makes a lot of sense, because the revenue then would be 0. So if he produces no doghouses, he makes no money. Another vertex was at 0, 3, meaning he produces 0 small doghouses, but 3 large doghouses. So 15 times 0 plus 20 times 3, his revenue would be $60. He had another vertex was at 3, 0, meaning he's going to produce 3 small doghouses, but no large doghouses. His revenue would be $45. The other vertice was at 2, 2, meaning he would produce 2 small doghouses and 2 large doghouses for a revenue of $70. So when you look at this, you want to look, you're looking for a maximum value, because it's revenue. The maximum value occurs at 2 small and 2 large doghouses. So that's what he should produce to maximize his profit. So let's take a look at the strategy for these linear programming problems. You're going to use the following steps to find the maximum or minimum value of the linear function subject to linear constraints. Step 1 is to graph the region that satisfies the constraints. 2, determine the coordinates of the vertex of the region. 3, evaluate the function at each vertex of the region, and 4, identify the vertex that gives the maximum or minimum value for that particular problem. So we have another example. This one says 1 serving of food A contains 2 grams of protein and 6 grams of carbohydrates. So we're looking at food A, proteins, and carbohydrates. The next part says that 1 serving of B contains 4 grams of protein and 3 grams of carbohydrates. It says a dietitian wants a meal that contains at least, so we want to have at least 12 grams of protein and at least 18 grams of carbohydrates. If the cost of food A is 9 cents per serving, so now we have a cost, and the cost of food B is 20 cents per serving, then how many servings of each food would minimize the cost and still satisfy those constraints? So again, let's take a look at setting up a table to understand this problem a little better. So we have food A, and we have food B. We have protein, and we have carbs. So when we look at this, 1 serving of food A contains 2 grams. I think we should identify our variables first. At the bottom it says how many servings of each. So let's let X equal the servings of food A. And Y equal the actual number of servings of food B. So number of servings of food A and the number of servings of food B. So proteins in food A, we get 2 grams. So 2 grams times the number, that's going to be 2x. And then in food B, we get 4 grams of protein, so that's going to be 4y. Carbohydrates, I get 6 grams from food A, that's 6x. And I get 3 grams from food B, so that would be 3y. Now let's go down to what the dietitian says she wants to have, and that's at least 12 grams of protein and at least 18 grams of carbohydrates. So now let's look at writing our constraints. Again, x is going to be greater than or equal to 0, and y is going to be greater than or equal to 0 because we're not going to have less than 0 grams of protein or 0 grams of carbohydrates. So we're again looking at that first quadrant as being the region that our graph will fall in. So now this one says at least. So my first equation is going to be that 2x, so the number of grams of protein times the servings of food A, plus 4y, the number of grams per serving times the number of servings, has to be greater than or equal to 12. So when we solve this for y, we get 4y is greater than or equal to negative 2x plus 12. So y is greater than or equal to minus 1/2 x plus 3. So we have a y-intercept at 3 and a slope of negative 1/2. So we can go ahead and put in that line. Okay, the next equation, we're going to have 6x plus 3y has to be greater than or equal to 18. So solve that for y. I have 3y is greater than or equal to minus 6x plus 18. So y is greater than or equal to negative 2x plus 6. So again, go ahead and graph that equation. And we're going to be looking for the region that satisfies those inequalities. So now y is greater than, so the region that would be greater than would be this region above those lines. So now I'm going to look for my vertices. I have one at 0, 6. I have one that looks like it is at 6, 0. And one that looks like it is at 2, 2. Okay. And the last thing I have to consider is my objective quantity, which is going to be related to the cost. It says if the cost of food A is 9 cents per serving and the cost of food B is 20 cents per serving, then how many servings of each would minimize cost? So let's write our objective quantity now. So I have my objective quantity. Okay, so I want to minimize cost. So I'm going to use C. So C of x comma y is going to be equal to the cost for serving A, for a serving of A, is 0.09x plus the cost of food B is going to be 20y. Now let's look at where our vertices occur. I have one at 0, 6, one at 6, 0, and one at 2, 2. Remember, we're looking for a minimum cost this time. So I have 0.09 times 0 plus 0.20 times 6, which is going to give me a cost of $1.20. For the next one, I have 0.09 times 6 plus 0.20 times 0, which is going to give me 54 cents. And the last one, 0.09 times 2 plus 0.20 times 2, which gives me a cost of 58 cents. So we're looking at minimum cost. So the minimum cost would occur at this vertex where you have 6 servings of food A and no servings of food B, but you're still meeting the requirement of the amount of protein and the amount of carbohydrates that the dietitian wishes you would eat. Okay, so that's our lesson on linear programming. Please feel free to read through the book to help clarify your understanding. We'll go over this again tomorrow in class, and we'll do the homework problems assigned at the bottom of the sheet. Thanks, and have a nice evening.